This presentation provides a practical guide to implementing Bayesian Vector Autoregression models, known as BVAR, using the EViews software. We will journey from the underlying theory of priors to their application in macroeconomic forecasting. This guide is tailored for students, academic researchers, and practitioners who use EViews 13 or newer. Traditional vector autoregression, or VAR, models face a core challenge related to over-parameterization. This means the number of parameters to estimate grows exponentially with the number of variables and lags. This issue is often exacerbated by having small sample sizes, as macroeconomic data series tend to be short. The direct consequence of having too many parameters and too little data is poor forecasting performance, characterized by large standard errors and overfitting, where the model captures noise rather than the true underlying signal. In essence, the core problem is that many parameters combined with little data inevitably lead to poor forecasts. The solution to stabilize the model and improve its performance is to introduce external information, often referred to as priors or prior beliefs, into the estimation process. This helps to constrain the model and make it more robust. The BVAR approach is particularly suitable when you have a short data sample. It helps to stabilize the estimation process where a traditional VAR would fail. It is also the preferred method for models with a large number of variables, as it effectively manages the parameter explosion problem. Crucially, BVAR allows you to formally incorporate economic theory into your estimation. For instance, you can set a prior belief that a variable follows a random walk, a common assumption for many macroeconomic series. The flowchart on the left illustrates this decision process. After starting with time series data, performing unit root tests, and selecting the optimal lag length, the key question is whether your data sample is large enough relative to the number of parameters. If it is, an unrestricted VAR, OLS, can be used. If not, Bayesian VAR, BVAR, is the appropriate choice, ultimately leading to impulse response analysis and forecasting. The fundamental principle of Bayesian analysis, as illustrated in the diagram, is combining prior beliefs with evidence from the data. The result is the posterior distribution, which is proportional to the product of the likelihood from the data and the prior distribution, our initial belief. The prior represents our belief about a parameter's value before seeing the data, while the posterior is our updated belief after the data has been incorporated. Shrinkage is the key technique here. The BVAR model systematically shrinks the estimated coefficients towards the value specified in our prior. This process reduces variance, helps prevent overfitting, and is particularly beneficial for reducing noise when dealing with small sample data, ultimately leading to more accurate forecasts. This slide outlines the common types of prior distributions available in EViews for Bayesian VAR models. First, the Litterman or Minnesota prior is the most frequently used and an excellent starting point, especially for beginners. It assumes a diagonal error covariance matrix and is ideal for basic forecasting with smaller models. Second, the Normal-Wishart prior offers more flexibility. It treats the error covariance matrix as a random variable, making it particularly suitable for structural analysis and risk modeling, especially when cross-variable correlations are important. Lastly, more advanced priors like Sims-Zha or Giannone et al. Have complex structures that involve optimizing hyperparameters and are typically used for in-depth research beyond a basic introduction. As a general recommendation, if you're a newcomer to BVAR, choose the Litterman Minnesota prior. If you need to perform sensitivity analysis or structural analysis, then the Normal-Wishart prior is the better choice. To begin, navigate through the EViews menu. Quick, Estimate VAR. First, ensure your work file is a time series work file, as Bayesian VAR is a time series technique. In the specification window, select Bayesian VAR. For the initial residual covariance, it's recommended to choose diagonal VAR, as suggested by Loot Cable. This provides a reasonable starting point for the estimation. This slide details the configuration of hyperparameters within the BVAR model. First, mu1 sets the prior mean for the AR1 coefficient. It is typically set to 0 or 1, depending on whether the variables are in levels or growth rates. Next, lambda1, or lambda1, controls the overall tightness of the prior. A smaller value indicates a stronger belief in the prior. The default for lambda1 is usually 0.1 or 0.2. If lambda1 approaches infinity, the BVAR model converges to a standard OLS VAR. Conversely, if lambda1 is set to 0, the coefficients are strictly forced to equal the prior mean. Then, lambda2, or lambda2, represents the relative cross-variable weight, determining how much the coefficients of other variables' lags are shrunk. Finally, lambda3, or lambda3, controls the lag decay rate, influencing how aggressively coefficients on more distant lags are shrunk towards 0. For our case study, we will use the well-known Cho and Moreno dataset, which is included as a sample file in EViews, cho-moreno.wf1. The dataset covers the period from the first quarter of 1981 to the first quarter of 2000. We will use 3 key U.S. macroeconomic variables: the output gap, GAP, inflation, INFL, and the federal funds rate, FF. Before running any VAR or BVAR model, a crucial preparatory step is to test each time series for stationarity using unit root tests. To start the case study in EViews, you would simply type open cho-moreno.wf1 in the command line. Then, you would perform an augmented Dickey-Fuller test on each variable, GAP, INFL, FF, to ensure they are stationary before proceeding with the model estimation. With our data ready, let's specify the exact BVAR model for this case study. This slide outlines the specific configuration for our BVAR model in EViews for the case study. First, we declare our endogenous variables, GAP, INFLA, and F. Based on information criteria, we've selected 2 lags for the model, specifically from lag 1 to lag 2. We will employ the standard Litterman Minnesota prior for this analysis. For the hyperparameters, we set mu1 to 0. This is a crucial strategic choice, as for detrended data like the output gap and inflation, the prior mean should be set to 0, assuming the variables revert to their mean, rather than 1, which implies a random walk. Lambda 1 is set to 0.1, indicating a strong degree of overall shrinkage towards the prior mean. Lambda 2 is set to 0.99, which heavily shrinks the coefficients on the lags of other variables. These settings are concisely implemented in EViews with the command var cha bvar.prior equals lit, mu1 equals 0, L1 equals 0.1, L2 equals 0.99, 1, 2, gap infla f. When you look at the BVAR output, the main coefficients shown are the posterior means. These represent the average value from the posterior distribution and are our best estimate for each parameter. The numbers in parentheses are the posterior standard errors. They measure the uncertainty or spread of the posterior distribution. A smaller standard error indicates a more precise estimate. A key benefit of the shrinkage mechanism is that these posterior standard errors are often smaller than the standard errors you would get from a classical OLS VAR, reflecting more precise estimates. The Normal-Wishart prior is an alternative that offers more flexibility than the Minnesota prior. Its key feature is that it assumes the error covariance matrix, denoted by sigma, is a random variable rather than fixed and diagonal. This makes it suitable for structural analysis, where the correlations between shocks to different variables are of interest. An important practical difference is that the Normal-Wishart prior has fewer tunable hyperparameters. Specifically, it does not have a separate lambda 2 parameter for the cross-variable weights, simplifying the setup slightly. Impulse response functions, or IRFs, trace out the effect of a one-time shock to one variable on the future evolution of all variables in the system. In EViews, you can generate them via view impulse response. Unlike in classical VARs, the confidence bands in a BVAR are generated using Monte Carlo simulation, drawing from the posterior distribution of the parameters. To interpret the chart, if the zero line lies outside the confidence band for a given period, the response is considered statistically significant at that horizon. It's common for BVAR confidence bands to be wider than their classical counterparts, reflecting a more honest representation of parameter uncertainty. Forecasting is where BVAR models truly excel. They operate on the principle of the bias-variance trade-off. By shrinking coefficients towards a prior, BVAR intentionally introduces a small amount of bias into the estimates. However, this process dramatically reduces the variance of the estimates, especially in small samples. The reduction in variance typically outweighs the increase in bias, leading to more stable and robust forecasts with a lower out-of-sample prediction error. This is often visualized using a fan chart, which shows the forecast probability distribution over time. Studies consistently show that the root mean square error, or RMSE, of BVAR forecasts is often lower than that of traditional VARs. When forecasting inflation for the next 2 years, a traditional VAR might produce a very wide and uncertain confidence interval. A BVAR, by shrinking parameters, would likely produce a tighter forecast band, a narrower fan chart, reflecting more confidence in the prediction, which often proves to be more accurate when compared to the actual data later on. While powerful, implementing BVAR models can sometimes lead to issues. Let's go over a quick troubleshooting checklist. This slide provides a troubleshooting checklist for common issues encountered when estimating Bayesian VAR models. If your impulse responses or forecasts look flat, with no dynamics, it's often a sign that your prior is too tight. The solution is to loosen the prior by increasing the value of lambda 1, for example, from 0.1 to 0.5. If you observe coefficient signs that are contrary to economic theory, you should double-check your prior mean, mu1. For stationary data or variables in growth rates, it should typically be set to 0, not 1. Lastly, if your model fails to converge, it could be due to a highly restrictive prior or insufficient computations. In this case, try increasing the number of iterations in the estimation options or generally loosening the prior. Always remember to check if your data is stationary, if your prior mean, mu1, is reasonable for your data type, and if your tightness parameter, lambda 1, is not overly restrictive. This slide provides a comprehensive summary of the BVAR workflow and a practical cheat sheet for implementing it in EViews. The workflow illustrates the sequential steps, starting with collecting and preparing your data, then proceeding to choose a prior to incorporate initial beliefs, followed by estimation of the model. From the estimated model, you can analyze impulse response functions, IRFs, and ultimately generate forecasts. The key message emphasizes that BVAR serves as an effective bridge, combining rigorous quantitative models with valuable expert economic knowledge. This unique integration makes BVAR particularly well-suited for robust macroeconomic forecasting. Below the workflow, you'll find EViews syntax examples for key operations. For a Minnesota prior setup, you can use a command similar to var bvar1.bvar prior equals lit, mu1 equals 1, L1 equals 0.2, 12yx, specifying the prior type, mean, and tightness parameters, along with the lag length and endogenous variables.